We are going to do a conservation of energy, what I call a sequence. And that's going from, like an object being at the top of something and then falling and seeing how the energy changes as it is falling. And if you notice, I have a little pun down here that it is an excellent example. First of all, what is conservation of energy? Conservation of energy is the idea that energy can be saved or it stays the same. And so the energy, total, I guess. So total energy in the beginning equals the total energy in the end. So whatever we start with is how much we end with. The types of energies will just simply transfer between each other. And those three types of energies that we will be looking at in these examples are potential energy, kinetic energy, and something called E-lost, which is energy that will be lost to the environment, usually in the form of heat or sound caused by friction or air resistance. If you need more help with potential energy and kinetic energy, please make sure that you go back and watch the videos on those individually. I am not going to go through those again. I'm just going to use them in this conservation sequence. So the first thing we're going to do is go to a simulation. We'll go here to what we call the skate park. And here at the beginning, we have a dog on a skateboard. And what you should notice is that all of the energy, the total energy, is in the form of potential energy. So potential energy. So then if I hit play, you'll see that as the dog on the skateboard goes down the ramp, so here he goes again, that potential energy decreases and kinetic increases. So at the top, there's more potential, and at the bottom, there's more kinetic. Something else you should notice is the total stays the same the entire time. Now, if I were to pause this, say somewhere here, just about at the middle, there is half potential and half kinetic. And that's because there is a height associated with our dog on the skateboard. If there is height, there is gravitational potential energy. Now, the dog is also moving. Of course, it's paused right now. But because it is moving, there is going to be kinetic energy. If you take that green and that blue bar, and if you were to add them together, they would equal this total again. Now, let's see, let's get them back up there and have them come back down to the bottom again. Ready? Ha ha. Here at the bottom, if we're at the bottom of the ramp, our height is 0. And if we have a height of 0, then our gravitational potential energy will also be 0. So if you notice in our bars over here, there is only kinetic energy. And so that total bar, again, the total bar never changes. That's what conservation says. That total bar is equal to the amount of kinetic energy. So how would this look in an example? The first thing that we need to remember, especially from the simulation we just looked at, is that at the top, all of the energy is in the form of potential energy. So that total bar is equal to potential. At the bottom, all of the energy is in the form of kinetic energy. So one of the first things that you have to do whenever you have one of these sequences is you need to find the amount of potential energy at the top. That is then your total energy in the system that you will use in the fall. So let's start a sequence. This one says, a child drops a rock out of a 2-story window. It takes 0.74 seconds for it to fall, assuming no air resistance. How tall is the window? Here is a huge hint. It says to use the projectile's unit to solve for distance. So why don't we go to the equation sheet and see what this is. There we go. All right, so in our projectiles unit right here. So this was the unit where we had x's, so dx, vx, and t, and then we had all of these y's, the dy and so forth. Well, we're looking for the height, and height is going to be dy. And so just like we did in the previous projectiles unit, the only one of these equations that we used to find dy was this one right here. dy equals VIYT plus 1/2 GT squared. So let's use that one. dy equals VIYT plus 1/2 GT squared. All right, let's see. Since our initial velocity, because our initial kinetic energy is 0, initial velocity is 0, therefore that whole expression goes away. So we have dy equals 1/2 GT squared. We have 0.74 seconds. That is our time. And so dy equals 1/2 g, which is 9.8, times 0.74 squared. Only that time is squared. So if we were to put that into a calculator, we would get 0.5 times 9.8 times 0.74 squared. Let's see, I got 2.68324, so let's just say 2.68 meters. So that is the height of our window. We're going to need that. The next thing that we need to be able to do is use the mass, because in both potential energy and kinetic energy, there is a mass component. It says here that the child then drops a 10 kilogram green toy soldier toy out of the window. Well, the reason why this is in grams is because our scales that we use in labs always measure in grams. Now, in the equations, we need kilograms. And so the first thing we are going to do is convert this mass into kilograms. Let's see. So in order to do that, it's going to be the number of grams divided by 1,000. So 10 grams divided by 1,000 gives us 0.010 kilograms. The next question here says, what is the weight of the soldier? In a previous unit, we talked about weight. Weight was a force. And so we would need to look in the force section of our equation sheet. And the way that I helped people remember which force weight was is that weight has a G in the middle. So let's go look. All right. So here's our forces unit right underneath projectiles. And since weight has a g in it, then we need to find the equation that has a g. And so that is FW equals mg. Let's use that one. All right, so FW equals mg. M here needs to be in kilograms. That's why we did this number 1. So 0.010 times 9.8. And if we multiply those two together, we get a mass of 0.098 newtons. Weight is a force, and so it's measured in newtons. All right, let's see. What's next in the sequence? So we found mass in kilograms, and then we found the weight. Oh, the original potential energy of the soldier. Well, let's see. Potential energy. Let's go back to the equation sheet. There we go. Let's see if we can find potential energy. Oh, there it is. Work, power, and energy. Potential energy. Oh, there it is. PE equals mgh. So let's use that one. Right. PE equals mgh. Well, to make it easier, so I don't have to keep flipping back and forth between slides, down here in the bottom, I actually put my height and my mass. So we'll have those easily accessible for this equation. So PE equals m, which is 0.010, g, which is 9.8, times height, which is 2.68. So we're going to multiply those three together. So 0.010 times 9.8 times 2.68. Let's see, I got 0.2626. And energy is measured in joules. Now, here's a little interesting thing. See how on this equation it's mgh? Well, in number 2, we found mg. Here, look. mg. So we could have just done the weight of the object, the 0.098, and multiplied it by the height. And we would have gotten the same answer. But those are two different ways you can do it. Either one is correct. Now, in number 4, it says, assuming no air resistance, what would be the kinetic energy at the ground? Well, what we saw in the simulation, I'll go back to where we wrote that down, is that the energy at the bottom is all kinetic. So however much potential energy we have in the beginning at the top is how much we will have at the bottom. So if we have 0.2626 at the top, then we will have 0.2626 joules of kinetic energy at the bottom. And since this is assuming no air resistance, this is an ideal situation. So in number 5, it says, what would be the ideal speed? Speed is, in terms of equations, interchangeable with velocity. So we're going to be looking for V. Well, let's see. What equation can we do that has V in it? Let's go look. So let's go to the equation sheet. And let's see. Oh, look, there's one. Kinetic energy Ke equals 1/2 mv squared. And we did just figure out the amount of kinetic energy at the bottom. All right, well then, let's use that one. We have Ke equals 1/2 mv squared. Well, we know Ke is 0.2626, and that's 1/2 times m, which I put down here, right? 0.010 times v squared. All right, well, let's do half of that number, right? So 2626 equals 0.005. My goodness, tiny numbers here, huh? Times v squared. Then to get v squared by itself, we need to divide by 0.005 on both sides. Let's see, so here we go. V squared equals, all right, 0.2626 divided by 0.005. And I get 52.52. Well, now what do we do? That's not v, because that's v squared. Well, we got to undo the square. That's a square root. And so the square root of 52.52 is 7.25 meters per second. It'll round up. It's 247, but I'm rounding up to 25. And that is perfectly acceptable. Let's see. So what is the next step in this sequence, huh? Oh, well, this is the last one in the ideal. It says, what would be the soldier's ideal momentum? Okay, well, that goes back to another unit too, doesn't it? So momentum was momentum, which was lowercase p. So let's go find that equation on our equation sheet. Let's see, momentum. Oh, here it is. Here's the momentum unit. And so there's our momentum equation. P equals mv. All right. Let's use that one. P equals mv. Still the same m. 0.010. And then v is 7.25 meters per second. So we're going to multiply those two together, and we get 0.0725. The unit for momentum was what I called a squish unit. And so you take the two units, kilograms and meters per second, and you squish them together. And so you get a kilogram meter per second. That's what Miss Parker calls a kigums. So it'd be 0.0725 kigums. There's our ideal. Now, what happens if there is actual air resistance or friction? Let's go back to the simulation now. So let's see, here's our skate park. And for this one, since it's a ramp, we're not going to do air resistance. Instead, over here on the right side, you see that there's friction. So I'm going to move it up to where there's about half friction. I'm going to pull our skating dog back up to the top. And the first thing you should notice is even though there's friction on the ramp, in the very beginning, all of the energy, the total energy in the system, is still entirely potential. Let's see what's different now. See, we're still getting kinetic. Oh, there's a red bar coming in. See, that red bar is called thermal. So as this dog on a skateboard is going back and forth on this ramp, that thermal is starting to grow more and more, and this dog is not going as high. That thermal component is what we call E lost. It is the energy that is being lost to the environment. In this particular simulation, they only account for it as thermal energy, which is heat. So it's the idea that if it's cold outside and you rub your hands together, they get nice and warm. And it's because the friction between your hands generates heat. And that heat is then released into the atmosphere. Now, if I were to restart this again, oh, no, get on the track there, silly dog. Go. And I'm going to let him go up the other side, and then I'm going to pause at the bottom. There we go. Here at the bottom, you'll notice that there's still not going to be any potential energy because we're still at a height of 0. So at the bottom, there is still 0 potential. But because of that friction, it's not all kinetic anymore. Instead, there is this thermal component. And so the thermal component in this simulation is what we're going to call E lost. So at the bottom of the ramp or the bottom of the fall, we'll have kinetic and lost energy. What you should also notice is if I were to take that green bar and that red bar and add them together, we still get the total. And that's because conservation of energy says energy in the beginning equals energy at the end. It doesn't matter what form it is. If you add all the different forms together, that total still remains the same. All right, so here we go. What happens at the top in a non-ideal situation? So this is one with friction and air resistance. Well, the top is still all potential energy. So you still need mass, you still need height, and you still need to find the potential energy, and that is still the total in the entire system. This time, though, the energy at the bottom is kinetic energy, but there's one more. It's that lost component. I prefer calling it E lost instead of thermal because sound is also a type of energy. And with skating and things like that, you can hear when the skateboard is on the ramp. And so if you can hear it, then there is energy that is going into the sound. And that's from the friction between the wheels and the ramp and in the axles and everything like that. And so the sound plus that heat is what is that E lost. So that's why I like to make it a little bit more general. So at the bottom, it'll be kinetic and E lost. So now let's go back to the sequence. It says now a paratrooper toy. That one's one that has a parachute. Has the same mass. So that was 10 grams. Falls out of the same window. So the next question is, what is the mass of the paratrooper in kilograms? Well, since it's the same mass, it would be the same mass in kilograms, which is that 0.010 kilograms. So that hasn't changed. What is the weight of the paratrooper? Well, gravity is still pulling down on it exactly the same as the one without the parachute because it's the same mass. So that's going to be exactly the same weight. It's still going to be that FW equals mg, but m is still the same and g is still the same. And so we still get 0.098 newtons of weight. Next one is, what is the original potential energy of the soldier? Well, potential energy was mgh. Just because it has a parachute, M hasn't changed, G hasn't changed, and H hasn't changed. It's still the same window. And so all of that is still the same. And so PE is still going to be 0.2626 joules. Oh, well, here's the difference. Here it says if it takes, go back. If it takes 2 seconds for the paratrooper to fall, well, that's a lot longer of a time. Previously, I think if I remember correctly, it was like 0.74 seconds. So this is over twice the amount of time. Well, if it falls in more time, that means it's going to be going slower. We expect that with something with a parachute, right? On Earth, where there's air resistance. And so that means the speed is going to be less than what we found before. That 7 number, this is going to be less. This equation, if you need to use it, it'll be given to you, just like it is here. So let's find that velocity when it hits the ground, which is its final velocity. So 2 times dy, that's our height, 2.68. See, I still have everything down here. Divided by time, which is 2 seconds. Oh, well, that makes it nice and simple, huh? So those 2's are going to cancel. And so our velocity will be 2.68 meters per second. Much slower than the 7.25 meters per second in the ideal scenario. Well, since it's going slower, what's going to happen to the kinetic energy? Well, it's going to be less. How much less? Well, let's find out. KE is 1/2 mv squared. Now, the reason why the answer is not going to be 0.2626 this time is because we obviously have some loss of energy, which is why this object is going slower. This paratrooper is slower, just like the dog was slower. KE equals 1/2 m 0.010 times v squared, so 2.68 squared. All right, let's throw that in the calculator. 0.5 times 0.010 times 2.68 squared. Oh, wow, that's a lot less. 0.0359 joules. Compare that to the 0.2626. Whew, that is a loss. Well, I guess that's going to be the next question, isn't it? Yeah, how much energy was lost? Well, at the top, right? The top, we had 0.2626. And at the bottom, we know we have 0.0359 joules of kinetic energy. So how much is lost? Well, loss means it goes away, so I bet we need to subtract. So 0.2626 minus 0.0359 is going to give us minus 0.0359. Let's see. I got 0.2267 joules. That is a lot of lost energy. How much power did the air resistance generate? All right, well, we need the power equation, don't we? So let's see. Let's find that power equation. Okay. Here we go. Power. That was up in work, power, and energy. Oh, there it is. Power is work over time. Let's see. So P equals W over T. Let's see. Well, we know the time is 2 seconds, right? So we'll put the 2 in at the bottom. Work. What work was done? Well, it's asking about the air resistance, right? So how much power did the air resistance generate? Well, that's going to have to do with the lost energy. So we're going to use that number, 0.2267. All right, so if we do that, we will get 0.113, and then we'll say, see, that would be another 3. So we'll just say 0.113, and power is measured in watts. It's not a whole lot of power, but it's still there. And then lastly was how much momentum. All right, well, the momentum was lowercase p. P equals mv. And so mass is still 0.010. Oh, what was our velocity? Let's go back. Velocity was, oh, there it is, 2.68. Okay, so 2.68 meters per second. And so we get 0.0268, and that's that squish unit, kilogram meter per second, or as Miss Parker calls it, kigums. All right, that is the end of the sequence. I know that's a lot. What you really want to make sure that you focus on is this non-ideal, because as it is an excellent example, you are probably not going to be an ideal situation there with some eggs. Therefore, focus really on the second part of that sequence.